neurosciences, as well as the clinical sciences. So I liken my role, both in practice and in research, as more like a clinician than a scientist, in the sense that when the doctor faces a patient, that person has an immediate need that has to be dealt with immediately with all of the best knowledge that we have. Similarly, when someone wants a building, that building needs to be created, and we can't wait to find everything that we need to know, but at no time should we let go of any of the methodologies. So I started in anthropology. I was swayed by one of the best neuroscience teachers on campus to go down the path of neuroscience, did that, wet bench, laboratory, intracellular research, and then went into clinical neuroscience, and then heard of the Academy of Neuroscience for Architecture, and I thought, ooh, that sounds interesting. And went back into my architecture degree. So what I actually want to do today is give you sort of a menu of the ways in which we've been applying that background to practice. But first of all, I have to ask about my audience. How many psychologists in the room? How many architects and designers in the room? Okay. How many clinicians in the room? Nurse through therapist, through doctor. Okay. All right. How many others? All right. Neuroscientists, engineers. Okay, good. All right. So when I talk about the brain as tinged design, I can respond to a smattering of you. And what I really should be saying, this is awfully simple and wouldn't it be nice, but it really is an adaptive complex system with a resting state far from equilibrium, tuned in space and time to respond to environmental stimuli. And wouldn't it be great if that was all we needed to know? But hard enough as neuroscience is, hard enough as clinical neuroscience is, now let's combine it with an understanding of architecture. And just to bring calm back to the effort, we can steal the phrase neuroarchitecture from the people who looked at the form of the brain and to discern its function, and take it to apply it to our own efforts to understand how the brain and mind and body interact with the built environment. And I'm often surprised that I have to remind people that the brain is connected to the body, and the system really doesn't work very well unless the two of them are connected. You know, imagine your clients asking you for a design and there's just a head, or the head is attached to a body. This just doesn't work. And so we finally, in Western medicine, come to the understanding that indeed we need to look at the feedback loop amongst the entire system. And one of the things that, as a sensory physiologist, which is where I began, gives a sense of calm, because we have metrics there where we can evoke very controlled responses using very controlled stimuli. And yes, I understand it's reductionist, but I don't know any scientists, I'm sure there's some out there, who don't also respond to an overarching hypothesis that they're seeking to explore. And just as we design one building and think about that building, that context, those users, in science, we might seek to answer one question at a time, understanding that the legacy of literature that's come before is what gives that result powerfulness in human beings. So one of the things that's very interesting to me in sensory science is that there's this really beautiful cartoon of a psychometric and sensory function, whereas what you see is here's the response. This actually happens to be threshold. Do I detect a stimulus or not? And you'll see that at first, as the stimulus intensity increases, almost nothing happens. So if I measure 1 unit of intensity change, I get almost no change in the amplitude of the response. On the other hand, as an exponential or linear to logarithmic function occurs, for 1 unit of change, the same unit of intensity change, I get a huge difference in percentage change in response. And then when the stimulus intensity gets louder again, you flatten out. And so we see this pattern in many, many systems. And what you can do is to take this and convert it into a tuning curve. So this particular stimulus, I have greater sensitivity than at a stimulus up here. So this happens to be hearing tuning, and somewhere between 1,000 and 10,000 hertz, I have a peak sensitivity less than 0 dB sound pressure level, I get a response. Whereas up here, even at 130 decibels, I get very little response. So indeed, we can see in different sensory systems and different cognitive systems and in multiple systems, these indicators of the brain being tuned. And so this is an image of vestibular or your balance system and your visual system having very specific responsiveness to the world. We know the brain is tuned because we talk about alpha waves, beta waves, delta, gamma waves. And the question is, what is happening, and can we discern tuning to some of the architectural and design principles that we've all been fascinated, well, maybe not all, but I sure was fascinated by, is, what is it about what some people call the sacred geometries, and certainly when we look back into philosophy of beauty and architectural principles that stood the test of time and actually stand up across multiple thousands of years and multiple cultures where they're trying to understand the geometries of space and why certain buildings appear to stand the test of time and appeal across cultures. And having started as an anthropologist and become a biologist, and I look and see that if something appeals across time and culture, that says to me, what's the biological basis of this consistent response? So when we look at this picture, we can imagine what the biological basis is. It may be man kissing woman. However, if we're a bit of an architecture science geek, then we might look at it like this. And look at how these lines absolutely line up with what's happening here. And we know that this wasn't posed and thought about in advance, but look at the intersection and the geometries of space and how they line perfectly even to the edge of her skirt and the moment of her calf. It's incredible. And wouldn't it be wonderful if architecture and design was this easy and that we had discerned the set point of our eyes to see the beauty of design. It is, as we all know, a little harder than that. At a certain point in time, you look at the efforts to search for these principles within, and you realize it's a bit like the use and abuse of statistics. If you keep applying a test and you still can't see a result, at a certain point you have to say these things are perhaps not related. And this is particularly so when we look at still photographs of buildings. So we've been listening to a lot of talks about the visual impact of design. The only time we actually experience architecture visually alone is in a photograph. The rest of the time, all of our sensory systems are responding. The temperature as well as the light, as well as the touch, and our proprioceptive sense of where we are in this space. And so I think we do ourselves harm by ignoring the other sensory systems. Because I don't know about you, but I certainly have memories of place that are supported by the sound. For me, it's the sound of walking on a wooden dock out to the ocean. Early memory, favorite sound. Without the sound of the footprint on wood, it's an entirely different experience. And so as we move from a flat 2D image of architecture and try to understand it, and move to 3D and the fourth dimension of time as we move through space, let's also think about our other sensory systems. And so we've begun this process of looking at architecture and testing our response to architecture at least in 4 dimensions. And so here you see an image of a study that we did on wayfinding inside of a virtual reality cave, where we used a traditional architectural system to create a model of that system, and we tracked where the person was in virtual space as we set them through a series of rooms that actually copied the building that they were in. And then we used a 256 electrode display, and this is actually just a different study, so you're not seeing the full electrode array, but to look at the independent components of the brain that have been correlated by MRI and other methods to the spaces that those brainwaves come from, to see whether or not we could discern whether a person was lost or not, and as form follows function in the brain, which part of the brain was showing us a difference between whether someone was lost or knew their way. Because we do know that we can't simply ask people why they like something or how they found their way. I was doing a project for the Naval Medical Center, and the campus is highly complex with all these underground warrens. And we were getting lost, and I said to my very tall military colleague, I said, what do you guys do when you're out in the ocean? How do you find your way? He just looked at me and said, we have gadgets. And so what we've done is started bringing these gadgets to bear. So this is at the University of California, San Diego at Cal IT2, Qualcomm Institute. And so we pushed in the entire building and then created a piece of software to record these electrodes in real time as people move through space. So I'm going to try to play you a very quick snippet of that video so that you can see what it looks like.
An EEG and an eye tracking system. Whoa. We're going to measure the effect that different ceiling heights have on me.
Now look up to the top of the wall. How do you feel as that changes?
You feel like a weight is lifting, like literally a weight is lifting off your head.
As the roof is raised, we see a transition from that high frequency activity to a lower frequency signal, and it generally indicates a more relaxed state. It's possible that the sensation of that ceiling going up causes his brain to transition into a more relaxed state.
Back to the center. Okay.
As the image of the roof gets lower, we see that Tom's signals transition from that smooth signal that we saw before to a more higher frequency signal, a more active, tense state.
In Britain, we have very low space standards for our housing. Our new housing is very small in terms of room size and the amount of space given over to people. What would you imagine? What impact would that have on people?
Well, when dimension becomes too small, then we know it ranges everywhere from this feeling of compression that's palpable to a feeling of stress and an impact on function. If we give more information about the subconscious, what the body and the brain are doing in response to architecture, we can start to inform design that serves the human to a greater extent. I think it's a brave new world.
So we've begun exploring, using these technologies, a number of questions. So one question we had, actually inspired by Tom Albright, who's a vision scientist, was whether or not the Salk Institute had a degree of success in terms of this courtyard because of its single point perspective. And whether that's what was drawing the eye and settling the mind, because it was feeding into this tuned, if I can say so, preference for that simple sight line. We look at this courtyard and we say, I understand, prospect and refuge, horizon. These are the reasons why we respond as we do. But we can't forget that there are these other systems that may be involved also. And so our effort actually was to put people inside of the cave and artificially change the perspectives. The other study that we actually spent, and actually, by the way, it's very complicated to change the artificial change of perspective in a virtual reality simulation because you've created a geometry and the simulation has rules about how it displays itself. And so you've got to battle with the simulation of VR in order to make that happen. But a more successful effort that we undertook was to take the Salk Institute, model it up to accurate scale, and then use some of the space syntax rules in terms of what draws a person into a space to travel down a path. So using openness and jaggedness and all of these measurands of why a person would move down a space, instead of working up in that iconic patio space with the beautiful horizon, we worked down in the stairwells and modified each stairwell and then did a control test where people stood in one place. You could go that way, you could that way, you moved down the path of preference, and then we surveyed them afterwards to understand why they moved in this direction. The really interesting thing you can see is this Tyler Hamilton, who did this for his master's thesis, and one of our professors, is she is leaning forward because the perception of movement is so strong that she actually feels she's falling into this space. And I had a couple of volunteers who had synesthesia, and they walked through this and said, "This is not a good experiment." I said, "Okay, why is that?" They said, "Because I can't hear the architecture." And so these are people for whom they recognize the tight link between the sensory systems and couldn't see it in visual terms alone. And so part of my clinical research was actually, in clinical service, was actually taking advantage of this system of the balance organs that feeds into the brain and moves the eyes, because the brain wants the world upright and in front of you. And if we put you on a platform with 6 degrees of freedom to see how you sway and disrupt the visual pattern in front of you, you'll start to fall. And so this is a trickle down from the NASA dollars that were spent to understand why NASA scientists lost their balance, or astronauts rather, and who would and who wouldn't after they came and went to space. NASA scientists happen to be party animals. My brother is one, so I have a sample size on this. So disco ball was the way in which this system disrupted your visual system while you tried to balance. And so what we can do is take the data from the tuning of the vestibular balance system, understand how many degrees off of vertical the brain typically sees or does not see, disrupt the visual system, and understand how the proprioceptive physical system is responding to architecture, and ask questions about how we design space, ask questions about how much light and contrast and specular pattern should we produce before we cause harm. So this was a school for children with multiple cognitive, visual, mental disabilities, as well as physical disabilities. The proposal was to put this specular screen on, the desert climate, wanted to shade it, give the students a place to practice walking. But this highly specular pattern is very similar to the disco pattern that I would use to make people fall over. And these students had multiple sensory disorders. And so we advised against it. We created a softer shape. Massachusetts recently reported enormous increases in fall risk with age. And so we can ask ourselves, again, how we design for how the system is tuned to give you a visual vertical, and how it informs your proprioceptive musculature and systems, because even if both balance organs are out, and you can stand up in bright light, and turn off the light, you will fall over. And so by understanding these clinical and sensory things, we can create design balance. There's much more we need to know, and one of the things that fascinates me is how we create a sense of awe. And here this guy has worked on this building for 5 years. It's been growing out of the ground. And you can see in his body posture both the inspiration of the structure and the need to look at it in order to balance. So here's a great example by Softy. It's a Salt Lake library. And you'll see that it's a building divided in two, so all the stacks are on this side, and the reading carrels are on this side. And then the public space is in the middle. So I was walking, we were visiting with a tour of architects, and I was walking through these carrels on the upper level, and you can see that these are not vertical by design. It's a really engaging building. So I was walking along with my colleague, and he said, do you have a pen? Yeah, okay. And he put it on one of the desks to see if it would roll off. He said, I don't think the floor is flat. And so I said, actually, I know why you think that. And we took one step, and there was a student studying neuroanatomy. And the book was open to the vestibular system. It was as if it was staged. And I said to the point and said, that balance organ is the reason why you're confused, because you are used to seeing these columns as vertical. And you're used to there being a right angle. And you see this, and now your brain is assuming that. And so we can ask questions about how we create a sense of excitement, awe, level of movement in a space with the movement of columns across the visual field, but also how we can solve problems like fear of heights. If we give ourselves that visual stimulus to hold on to, we can overcome some of these issues. One of my master's students did a project on the space station, for a space station, not on a space station, because I would totally kicked him off that project and done that myself. But he had designed this beautiful symmetrical system. And I said, you can't. They have no gravity. They need every ounce of visual vertical you can give them, top and bottom. Make it asymmetrical so that you can give the visual system just that bit of stimulus, even though the vestibular and the gravitational systems are receiving stimuli. Now, can I prove that that would have an effect? Only by going back into the literature that exists on how the brain balances. There's a lot there. But also we can use the principle of do no harm. So if I look at literature, I look at clinical, I make a design principle, will the interpretation and translation of that design principle cause harm? And if my answer is no, then I feel comfortable in recommending it as a principle that the designers can embody. So if I'm in the balance organs, I better move to the cochlea, because that's where I began my studies. And full disclosure, my father was an architect. So I sort of grew up thinking about shapes and forms and structures. And the cochlea is one of the most fabulous structural systems you can find. So what you see here, well, in my humble opinion, what you see here are a set of, these are the cells that are the sensory cells that are part of the hearing system, and they're on a cantilever. And they're supported by pyramidal structure cells, which these are part of. And on those pyramidal cells are these outer hair cells, which were always thought of as a little odd, because the sensory cell is over here, the inner hair cell. That sends most of the fibers up to the brain. These ones don't send as many fibers up to the brain. So what are they doing? But they actually send feedback fibers from the brain out to the sensory organ itself. They're controlling the sensory organ. They're balanced on a pyramid, sitting on a cantilever. They have muscle fibers. They actually control the movement. They change the tuning of this organ, of the cantilever on a set point. So they pull it down or up and change the oscillations. So the brain is changing the sensitivity of a sensory organ. And if you're not sure this is true, check out my favorite Science Geek video.
1, 2, 3 o'clock, 4 o'clock, rock. 5, 6, 7 o'clock, 8 o'clock, rock. 9, 10, 11 o'clock, 12 o'clock, rock. We're gonna rock around the clock tonight. Put your glad rags on. Join me home. We'll have some fun when the flashlights work. We'll rock around the clock tonight. We're gonna rock till broad daylight. We're gonna rock around the clock tonight.
Okay, so Jonathan Ashmore, the little shadow you see here is a needle. It's a patch clamp. transducing the music into electrical systems, and this cell is responding. And until this and a few other pieces of evidence, it had been assumed that this system wasn't tuned by the brain, wasn't controlled by the brain. It was stimulus, input, up to the little man in the center of your head, and then you could behave. But what we now know is that the central nervous system, your memory, your sensitivity, the set point changes how the sensory organs act. And so here you can see that stimulating from the brain down, if it's low frequency, you have almost no response change. At a higher frequency, it reduces the signal from the cell in half. And so just as we've learned with neuroplasticity that our experience and exposure changes our brain, our memory and tuning changes our sensory systems. And so it's fascinating to me, some unusual cases where anecdotally we can see this happen, but it begs questions. So this is St. Coletto's school in Washington, D.C., which is a private partnership that created a fabulous school for children with multiple disabilities. They were unable to be mainstreamed in regular education. Michael Graves did a building and he broke all the rules. If you go and read, for example, the California guidelines on how you create a school for children with autism or special needs, it's everything different. They recommended it with bland walls and a tiny little chair with no distractions and a tissue box on the table because it was crying a lot. But here is their main corridor. And we can look at that and say, oh, I bet that thing resonates and reverberates like nobody's business. And it does. So I asked the principal, who happened to be a speech-language pathologist, so she had some training in language as well. And I said, how do the kids react to this? Because many of the kids with autism will be hypersensitive. She said it was fascinating. On the first day of school, we told all the children, you can go wherever you want, do whatever you want to do, but just, don't be mean to anybody. She said what the children who were hypersensitive to sound did was run through this lobby, making sounds, and essentially echolocating, finding out where the reverberation and the noise was within the space. And she said, I've not seen any of them. Need to do that again. Now that's pure anecdote, but fascinating nonetheless. But it begs us to say, all right, what can we learn about our own built environments that take advantage of what we know from both clinical and sensory science and start measuring what distracts the brain. So here we are using a standard psychometric test on creativity, trying to see a baseline that showed someone moving into the creative zone with this EEG system. And we didn't get it, but we got something even better. So the moments where you see these spikes in both alpha and in gamma, in this case, waveforms, is during interruption. So I think the experimental paradigm was flawed. We didn't give people enough time to go into creative mode. So I'm not surprised it's flat. But at interruption, things were disturbed to the point that don't relate to movement. We tested that out. So this issue of distraction is how we can start to understand with very simple technologies and create protocols that we can test in real space. So we know this matters. The relationship between sound and stress is increasingly well documented at much lower levels than is mandated by OSHA. 80 decibels if you have more than 8 hours of noise. Over 80 decibels lead to noise-induced hearing loss. Here I'm measuring impulse responses. And this arrow is between 110 and 120 decibels of impulse sounds at shift change in the hospital when every nurse and doctor was telling the new shift what was wrong with that patient. Because everybody was speaking about the level of the EKG alarms, the ambulance in the bay nearby, etc. So there's no surprise that we end up with an enormous amount of medical errors, in particular the sound-alike medication. So again, enough